Hey kids, welcome back to Mr. Murray's Math Land. We are learning yet another derivative rule today, a major one called the chain rule. So the time when you will need the chain rule is when you're trying to take the derivative of a composite function, which is when you have functions inside of functions. So if you were to look back at all the things you've taken the derivative of so far, like the square root of x, sine of x, cosine of x, e to the x, it was always just a plain old x on the inside of that function, whatever it may be, the cube root of x, the sine of x. But what if on the inside of the function there was another function? What if it was the sine of x cubed on the inside? What if it was the square root of cosine of x? What if it was e raised to the square root of x instead of just plain old x? And those are functions within functions. That's a composite function, and that's when you need the chain rule. So here it is basically. If you have a function, and this is just representing this composite relationship, notice that's f of g of x. That's not f times g. That would have to be f of x times g of x. But if you have a composite function, then its derivative is f prime of g of x times g prime of x. So notice that the idea is this. You start with the outermost function and you take that thing's derivative. The derivative of f is f prime of that same inner function. You know, g of x doesn't change there. And then you multiply by the derivative of the inner function. So it takes a little practice, and you see a bunch, and when you see real examples, hopefully it clicks a little bit better. But work your way from the outside in. And so here you go. Now take a look at this derivative right here. Doing the derivative of 5x cubed minus x to the 7th. Now you could use Pascal's triangle if you want to expand that out like a true maniac, and then do the derivative with the power rule, but the chain rule allows you to sidestep that. And it's to see that it's a larger idea of something being raised to the 7th. Hey, I can take the derivative of something to the 7th. I've taken the derivative of x to the 7th a million times, right? It's 7x to the 6th. So I'm going to use that idea here. The derivative y prime will be, and the derivative of something to the 7th is 7 times that something to the 6th. And that something in this case is 5x cubed minus x. And now is where you need to multiply by the derivative of the inner function. So each function's derivative does get represented, but it's a very particular way in which to do it and to get that routine down. So we multiply by 15x squared minus 1. That is the derivative of the inner expression. And make sure to use parentheses around that to show that it's all being multiplied by this. And that's it. That's done. You can, if you like, again, expand it or something, but there's no negative exponents. It seems fine to me. Okay, y equals the square root of 6x minus 5. Well, again, picture this as 6x minus 5 to the 1/2. The outermost function is the 1/2 power. I know how to take the derivative of something to the 1/2. Right? The derivative of something to the 1/2 is 1/2 times that something to the negative 1/2. 1/2 of that same something, 6x minus 5, to the negative 1/2. And now we multiply by the derivative of that something. The derivative of 6x minus 5 is 6x. Now we're definitely going to clean this up a little bit. Not going to leave a negative exponent. And I can do 1/2 of 6x. 1/2 of 6x is 3x. So I get 3x all over, and I move this to the bottom. And if you want to change it back to square root or leave it as the 1/2 power, that's fine. But there it is. Looks a little nicer there. No negative exponents. And 1/2 of 6x gave me that 3x up top. Very nice. So there's two chain rule examples. Now let's see some with trig. Trig is where you see a lot of this going on, because trig functions are not often just plain old sine of x, cosine of x. Oftentimes there's something else on the inside. But with trig, it's important to really see what is the outermost function and what is the inner function. And when you see sine of x cubed, you need to understand that notation, that what's being cubed is not the sine, it's just the inner x, the x is being cubed. So it's the sine of x cubed. So the outermost function is sine, so that's what I start with my chain rule. No problem. What's the derivative of sine of something? Cosine of that something. And now we multiply by that something's derivative. And the derivative of x cubed is 3x squared. And you probably, let's face it, would write this more as a coefficient. It looks a little nicer. And if you don't put the parentheses around the x cubed, that's okay. If you like to emphasize it, fine. But there you go, very nice. A lot of people, when you get the hang of the chain rule, they'll start just seeing it and just starting right out with, boom, 3x squared cosine of x cubed. But try to get that routine down of, hey, it's the cosine of that same thing times that something's derivative. And I put this example side by side so you can see the difference. Notice this is sine cubed of x. And this notation in trig means, what is it that's being cubed? It's not the x, it's not the angle, the argument that you're plugging in. It's the sine of that angle. So there's really, if you want to take a step and rewrite it, what you're really dealing with is sine of x being cubed. And that means in this case, when I go to do my derivative, the cubed is the outer function. So I'm back to doing like a power rule like I did on these ones. So, and that's one of the most commonly messed up things with chain rule is that order of operations. What's the outer function? So the derivative of something cubed is 3 times that something squared, and then multiplied by that something's derivative. What's the derivative of the inner function, sine of x? Cosine of x. And I suppose that would look okay, but really, come on, we're professionals now. We know we don't really leave it this way. We write it as sine squared of x, and that cosine of x could be right there. Looks a little tighter that way. But that's an important example to see those two side by side. It's all the same characters, it's same exact letters, numbers, variables, but you move that there to there, it changes the problem very much so. All right, number 5 here. Yeah, I got 12, but only to see a wide variety. If you want to stop at any time and just try it and see if you get the hang of it and then watch me do it, that'd be a great idea. But if you want to watch a couple more, go for it. F of theta is cosine of 5 theta squared. Again, what's the inner, what's the outer? The outer is cosine, so that's what I deal with first. What's the derivative of cosine of something? Negative sine of that something. And then we multiply by that something's derivative. What's the derivative of 5 theta squared? 10 theta. Remember, theta is just a variable. And multiplied by the negative out in front, you probably would make that a coefficient and make that negative 10 theta sine of 5 theta squared. Oh, nice. And here we go. F of theta equals cosine of sine of theta cubed. Ooh, we have it's like a nested, like one of those Russian nest tiles. We've got this inside of this inside of this. So this is going to be a double chain rule, but the outermost function is cosine. You just be patient and work your way there. What's the derivative of cosine of something? Negative sine of that something. And that something in this case that was on the inside of cosine is sine of theta cubed. Okay? And now, of course, times the derivative of that something. The derivative of that something, well, that something is sine of theta cubed. So you're doing the derivative of sine of theta cubed. That requires its own chain rule. The derivative of a sine of something is cosine of that something. Cosine of theta cubed. And then, of course, multiplied by that something's derivative, 3 theta squared. So there's the double chain rule, like I said. If you see that there's a cosine with a sine on the inside of it, with something on the inside of that other than just plain x, you know there's going to be 1, 2, 3 derivatives that get represented, and you got to go in that order, basically. When you multiply by the derivative of that innermost function, that's your last step. That's when you should be done. And I will put this together to make it look a little nicer, but double chain rules are tough. And put this all together, maybe make a nice coefficient of -3 theta squared, but then this is just ugly. It's the sine of theta cubed, and it's times cosine of theta cubed. And there we go. All right, so how about a little e action here? H of x equals e to the 5x squared plus sine of 3x. Well, what is our derivative of e to the something? The derivative of e to the x is e to the x. So the derivative of e to the something is e to that same something. Just like when we go, hey, e to the x stays e to the x. Same idea. So we get e to the 5x squared plus sine of 3x. But now you have to multiply by that something's derivative. You see, this is really this function on the inside of the e exponential function. So now I have to multiply by the derivative of that exponent, which would be 10x plus, and now I've got to do the sine of 3x. Notice that's not just plain old x. That's going to require its own chain rule. The derivative of sine of 3x is cosine of 3x multiplied by the derivative of 3x. And so I would be multiplying by 3. I'll just put it right there, though. And that's it. And notice it's just that part that gets multiplied by 3 because you were doing the derivative of sine of 3x at that moment. It's not like the whole thing gets multiplied by 3. So it's very, very tricky handling this. It takes practice. And people still, mishandle it. There's not really any great simplification here. I could have just really boxed that. Yeah, whatever. I'm basically going to rewrite it. I already started. There we go. Now this, you should recognize this as just an old problem. This is nothing special here. This, I mean, you could use the quotient rule, but you really should be able to just bring this up and say, hey, that's -2 times x to the -5, and use a power rule on that. Y prime is positive 10 x to the -6 when you subtract 1, and you move it back to the bottom. 10 over x to the 6. Easy, right? And just to, really the reason I did that was to draw this parallel between these next two examples, which are also fractions. And if you have -2 over e to the x, you could use a quotient rule on it, but you could also do this, -2 e to the -x. And you see, now that we know the chain rule, I can handle e raised to other things. Even though that's a -x, if it's anything other than just plain old x, it requires a chain rule. And so even just doing this requires it. So y prime is -2 times, what's the derivative of e to the -x? E to the -x multiplied by the derivative of -x. The derivative of -x is -1. So that will actually make +2 out in front. And I could leave that if you like. It's not a negative number. It's not a negative exponent. It's a variable. The variable itself could be negative or positive in making that. You could leave that if you want to move it back to the bottom because you feel like you should. Go for it. But yeah, notice you could use the chain rule on e to the x, for example, or any of these. Like the derivative of e to the x is e to the x multiplied by the derivative of x, which is just 1. Sine of x is cosine of x multiplied by the derivative of x, which is just 1. And that's why you don't need it really on anything that's just got x on the inside. But if it's got negative x or anything else, chain rule time. All right, number 12 here, last one. Very similar to the last couple, we've got negative 2 over something, and quotient rule would be fine, but you could bring this whole quantity up. Now that you know the chain rule, you can bring that whole quantity up and call that the negative fifth power, and our derivative will be just doing the power rule with the chain rule on this. So negative 2 times something to the negative fifth, that's nearly identical to this one, except instead of x, I've got this quantity. We get positive 10 x cubed minus x to the, subtract 1, we get negative 6. But now you have to multiply by the derivative of that inner expression. Derivative of x cubed minus x, 3x squared minus 1. Keep that in parentheses. I'm going to move this back to the bottom. 10 doesn't have a negative exponent, stays right where it is. 3x squared minus 1 stays up top. Move that to the bottom. X cubed minus x to the 6th. And there we go. All right, so a wide variety of chain rule problems. Hopefully the more you saw, the more it clicked, but you can go back, watch any, ask questions if you have any, and just keep working at it, because it's something that it takes a while to really get the hang of. So don't get frustrated if you don't nail it on the first couple problems, okay? All right, kids, have a good day.